Good afternoon, everyone. Okay, so I'm Emmanuel, also Ahenkan, and as I've been spoken about, I've done a lot of things in machine learning. Uh, so I've done masters in African Institute of Machine Intelligence, which is called AMI. After that, I've done a couple of internships outside Ghana, and I've also done a lot of researches in this field. Yeah. Okay, so whilst we're waiting for the presentation, uh, what I would say is I was here quite early, so I've heard a lot about other presenters, and I think they've given us the basis of machine learning, AI, and I think it's very good. Yeah, and I think it's very good. So currently what I'm coming to do will be to also give my part, which is an application of machine learning in the field of medical imaging, basically in the health sciences. Okay, so that's what I'm coming to do. So basically, what I'll be talking about is self-supervision. So I think yesterday and today we've done a lot about other types of machine learning, where we have the supervised, where it involves label data, the supervised, which does not involve any data. And I think the first speaker also talked about semi-supervised learning. But basically what I'll be talking about will be self-supervised learning. So basically self-supervised learning is you allowing your model to label the data itself. So you are learning from the data itself. So why is this really important? It's really important because in this real life, there are issues of data scarcity, and that's especially in medical field. But if there is data, like natural data, which involves, let's say, cars, these natural images and videos, those ones are also a lot. And with this kind of abundant data, it's kind of complicated to label it because most of them are not labeled. And if they are not labeled, it means that you need a person to annotate or label it. So this comes with two challenges. One is time consuming because people have to spend a lot of time to label this data. And two, the people labeling it will take money from you, which is also cost effective. So what self-supervised learning does here is to be able to, the model to learn from itself by labeling itself. So it's kind of limit the intervention of humans and stating it. So the data will label from itself. Okay. So then that's what I'm doing. And this is also very important in medical imaging because it's one of the fields that a lot of people are really sensitive about. Because let's say you assume a doctor or a health service company or like a service giving out public data or people's data, which is mostly confidential. So mostly we make use of the limited amount of data we have. We have to really make use of it so that we can actually work with it. So my work basically is on self-supervised learning, and self-supervised learning has two approaches. The first approach we have is a proxy task. Then we have main task. What the proxy task does is the task that we solve to learn from the data. So what it does is giving any kind of architecture that we've been since morning. It can be a convolutional neural network. It can be a multi-layer neural network. It can be any of the models we've discussed. It can be an autoencoder in the first speech. So what you do is you feed data to this kind of proxy task. Then after solving the data, then you fine-tune the main task. So self-supervised learning has two. First is a proxy task, and the second one is a main task. Okay, so that's basically what it talks about when the slides are being presented. Okay, so that's how it is. Okay, so the topic, as I've been talking about, is self-supervision via triplet loss in medical image segmentation. And this work was done by me and Professor Malin and Shuain Chan. They are all in University of Copenhagen. Okay. So what's the motivation behind this kind of research that we did? We found out that the units, I'll talk about the architecture known as units. We want to know how the unit performs. So we did experiment with the unit, and we found out the outcome of it, which I'll also show. So our motivation is, what can we do to improve the performance of a unit which is used for image segmentation? So we said that by using self-supervision, we will be able to learn better from the proxy tags, which will be now transferred as a form of transfer learning to our main tags, which is the unit, so that the performance of our model will increase. So that's what we did. So that was the main motivation for us trying to apply self-supervision in medical imaging. Okay, so in this self-supervision task that we were trying to solve, we found out that it was related to some works that have already been done. And that field is called contrastive learning. So basically, contrastive learning is a kind of association kind of learning. So we group similar objects together. So images that are similar, we group them, and images that are not similar or they are dissimilar, we separate them from each other. So that's what the basically idea of contrastive learning. And it's the normal, or what should I say, the ordinary kind of thinking of humans. Because if, let's say, a child is born and he sees a cat, first of all, he doesn't know what a cat is. But once he sees a cat, the next time he sees an object, he will try to relate it to what he has already known. So this one looks like something I knew, which was a cat. So it will be in a family of cats. You see something with a different features, and maybe it's a dog, you know that it's not similar to what a cat is. So it's an associative kind of learning where we group similar objects together, and some objects that are not similar, we try to separate them from each other. So that's what the contrastive learning try to do, is find similarity between objects. Okay, so then we come to the contrastive self-supervised learning. So what it does is, it's just as I said earlier on, but now we are adding the supervision to it. So what we do is, we have something we call the anchor, the positive and the negative. The anchor is our image that is under consideration. And the positive is an image that is similar to the anchor, and the negative is the image that is separate or different from the anchor. So the anchor can be, let's say, a cat, and the positive will be another breed or another kind of a cat. Then the negative can be, let's say, a dog or any other object. So this is what we try to do. Okay, so with this kind of contrastive learning, which is like a logical reasoning form of learning that humans being used, different works have been done under this. And the first, one of the initial forms of this contrastive learning was the CPC, which is the contrastive predictive coding. What this does is, I want to summarize it, whenever you have an image, it tries to break it down into sub-patches. So you have an image and you perform an augmentation on it. So the augmentation can be a color jitter, a grayscale, random flip, horizontal flip, all these kind of augmentations. Once you perform it on it, then you can crop or divide your images into sub-images. Then out of these sample images, you can use some of them as your anchor, your positive and your negative, so that you can do these tasks. So this was one of the initial basic ideas of contrastive learning. Okay, so the second one is also called the augmented multiscalar deep information maximization, that we call the AMDIM. So what this one also does is, they are all contrastive learning methods. What this one does is also applies these augmentations that have been there, the random jitter, the random grayscale, and random flip. After that, the most important thing about this is that given two images, there are important information or features that are inside every image that needs to be learned. So what this method does is it maximizes the information between images that are similar. So if there's a cat and another kind of a cat, what we try to do is to maximize the kind of information we are getting out from it. Then if there's another object, let's say a dog, we try to minimize the information between that cat and that kind of dog to show that they are the similar images. That's how I did. And similarly, there's the simple framework for constructive learning. That's called the SimCLAIR. It also uses similar approach where we divide the images into subgroups, and it does the same thing. Learn the features. So the important features in each image should be learned, and the ones that are closer or similar should be grouped together, and the ones that are not similar should be separated. So that's basically all the ideas about constructive learning, and people have done a lot of works in this field. Okay. So what we decided to propose was to use an idea of triplet loss to also do a kind of constructive learning. So what the triplet loss does is we can see here if this is the anchor, sorry, this is the anchor, this is a negative, this is a positive. So if this is our diagram, our ideology that we have here, after passing our images through our model for learning, at the end of the day, what we want to achieve is the anchor must be closer to the positive and the anchor must be far away from the negative, which shows that there are similarities between these two images, and the image over there, it's not similar to our image that we intend to do. So this is how the triplet loss does. So the A, as I've explained previously, is the anchor, which is our image of interest. The P is our positive, which is similar, and the N is the negative. And our goal is to minimize the distance between the anchor and the positive and maximize the distance between the anchor and the negative. Okay, so this is our pipeline that we propose. So from this side, we can see the A. We pass the image through an encoder. I think an encoder have been explained previously. It's just these neural networks that we are trying to deal with. We have autoencoders, an encoder, and a decoder. So the positive is also passed through an encoder. The negative also passed through these kinds of neural network. And the information or the weights are being shared among the encoders. Then after that, the output coming from each of these models, the encoder, we compute the triplet loss on it. So that one will serve as our proxy task. Then our main task will be to get the inputs, we pass it through an encoder, then we get it through a decoder, then we get an output of it. So let's say we have an image of a cat here, we pass it through an encoder, a decoder, then at the end of the day, we get an output which will label it or give us an output that we know it to be something similar to a cat. So this is our framework that we did. But what examples that I'm using is not in medical images. So let's use an example that will be beneficial to us in the steps slides below. Okay, so the main architecture that we use is called UNet. It's not anything really strange. It's just like the models the first speaker and the second speaker have been talking about. They are just normal neural network, but this kind of neural network we call the convolutional neural network. What it does is we have the downsampling side, the ones going down. Then we get to this embedding layer, then we maximize it. We do something like a deconvolution. So we have the upper part, which is like the deconvolution part. And you see the lines coming here. The information, they are called the skip connections. There's a skip connection between each of them, where information are being transferred from the deconvolution side, from the convolution side to the deconvolution side. And this is how the architecture is just a neural network, but they put it in this architecture and they call it a unit because of the shape. We downsample and upsample. Okay, So then we have an idea about how this contractive learning works, right? So to generate our positive anchor and our negative, we thought as a group to use an ideology that a lot of people have been using in medical imaging, which is called elastic deformation. So what elastic deformation does here is we want to distort the image a bit and feed it to the model and try to know if the model will still be able to recognize after small deformation. So this is so because our main images that we use, they are MRI images. And sometimes when you are taking the image of people, people are not really at one place. People might be moving where the image might not be the exact as we expect. So we try to distort the image a little and see if it will help us in improving our methods. So we use that method called the elastic deformation. And what this elastic deformation does is like it kind of take each pixels and kind of disperse it around using ideology of normal distribution with a certain kind of sigma where each pixels will be separated from its original position. So then after doing this deformation, we apply it on our input images. That's what we do. Okay, so for those people who like mathematics and want to visualize it in a mathematical way, this is the mathematical representation of triplet laws that we are trying to use, right? So we are just trying to find the maximum of that distance plus a certain constant, which is an alpha, and 0, right? We are just picking a non-negative number here, as you want to see. So, and that distance is just a Euclidean distance. We are just finding a Euclidean distance between the positive, the anchor and the positive, and the anchor and the negative. So this is basically it. The alpha is just there so that it will regulate this number so that we will not get any negative. Definitely, we will choose that number ahead of 0 because it's non-negative. So this is how this mathematical representation of the triplet law is. So once our goal is to minimize our loss, because in machine learning, you have a data, you put it through a model, then we get an output, then we compare the output to the ground truth. The ground truth will be the original data that have been labeled. So our goal is to find the loss between, or the difference between the original image and the predicted image. And then we want to reduce it. So our loss has to be as small as possible so that we can achieve our goal. So this is basically what I said. The cost function is just like the loss function. That our own main objective is to minimize this loss. Okay. So summary of everything that I've been trying to say, I want to make it short. We have a positive, an anchor, and a negative. We apply elastic deformation. Our goal is to learn the representation, the features that are important in our data. So we know with images, it's quite different from raw data, like let's say prediction data, which involves sales and let's say house prices. Here you feed into an encoder. What it does is first it will learn the edges. If it's a cat or any image, it will learn the edges. Then it will learn important features. If it's a cat, maybe the eye, the nose, the mouth, to learn that. Then at the end of the day, it will learn the classification part, which will predict the actual kind of class the image belongs to. So that's what I've said over there, and we compute the triplet laws. Okay. So now this is all the theory behind this, and we started with experiments. So we did a lot of experiments. So we tried a lot of diseases, but I think the one I will talk about will be a disease that we know as white matter hyperintensity, which is a data set we got, which was made in 2017. What these images are they are positive and negative images. So it's just like MRI images from patients, and mostly it's a brain image, right? So, and mostly this kind of disease is mostly found in elderly people people who are very old or senior citizens, as we say here. So once they come to a hospital and they try to tell us about symptoms or the issue that they have, what we do is we try to take MRI, then there are parts, or they call the lesions, a disease area which is mostly brighter than all other parts. So once we discover that these parts are more brighter, there's a higher possibility that the person has this kind of disease. So these were the data sets we work with, and it's kind of data that were around 60, but because of our augmentation, as I said, limited kind of data, with our augmentation and other things, we'll be able to multiply it. But we divide it into 30 for training, 20 for validation, and 10 for testing. That's how we did a lot of experiments with this kind of data sets. Okay, so I've already talked about this. Our image one, if we are considering 2 images, our image one that we feed in will be the anchor. Then we deform it to be similar. The same image, which is the anchor, we deform it to be our positive. Then we pick another image that is totally different. We deform it, that will be our image 2. So this is how we used to get our anchor positive and negative for our triplet loss. Okay, so after a series of experimentation, trying to do dropouts, using all the application of machine learning with different learning rates that we tried on, we were able to see that the units that I showed at Architecture, which is the baseline, gave us a DICE score. Here, the DICE is a similarity measure, which measures a similarity between images. So it's a similarity measure. In other places, people can calculate it as the accuracy or something. But in medical images and with the segmentation and reunits, we call it as a DICE score, which is a similarity score. So we had 0.77. Then we use our method, which is self-supervision, but without the elastic deformation, we had around 0.8, which is like an improvement by using self-supervision on the actual baseline, which was 0.77. So at least we were able to get some improvement using our technology, using our ideas that we came up with, which was quite okay. This is just the mean score. Sometimes it will go higher, it will go up, but this is the mean. Okay. So using the deformation that we talked about, trying to distort the images, we found out that these are averages. The triplet loss, when you deform the images so much, the network is not able to do the correct prediction. But if you do a small deformation, it's able to predict better. But we also did a study on and find out that maybe the deformation will not help us a lot because we don't have so much powerful models or ideas to really tackle it to our perfection. So there's been more steady working on this to know how we can use elastic deformation to its perfection. But for now, the best model that worked on was the triplet loss with no deformation. That's what really worked for us. Okay, so these are some of the images that I really wanted to show, sample of them. So you can see the T1, so these are the MRI. You can see from figure 1, the distortion was so much that even you can't really see. So definitely, as we said in the morning, if you feed your network with a really bad image, bad data, you are really going to get something that's not satisfaction. So here, the deformation was too much, which definitely will affect the accuracy or the DICE score. But when we perform a normal or a minimal deformation, small distortion, at least we're able to get something better than the huge deformation. Okay, so, and this is one of our results. So we can see this one. And this was our ground truth, which was the original image that was taken from a patient. And this is the predicted one. It's not really the same, but this model was able to predict it quite better. than this one, which looks really similar because the accuracy was around 80, almost 81, so this is some of our results, and out of all the experiments we try to do. So this is the conclusion part of our work. We found out that on the white matter hyperintensity data sets, trying to apply self-supervision actually increased the performance of the baseline units. And also we found out that when the deformation that we try to use is so high, our performance drop. But if the deformation is quite low, the model still work. But more research needs to be done on this approach. So someone might ask, what is the importance of this work? Why are we doing all these stuffs? So this work will actually help radiologists. Let's say a patient comes to the health center and you take the MRI. When this model, assume is perfect and being deployed, which is being worked on now, if it's being deployed onto devices like a computer or let's say a mobile phone, normal mobile phone, we can compare the image of the patient that came in to, we can feed it to this model, and the model will segment if there is kind of lesion or disease in the patient. This is just to help radiologists to confirm the kind of disease they see in humans, because we are not perfect and we can make mistakes. So you can come to me, I will tell you, oh, this is okay, you are not sick, but maybe you might be actually sick. Or I can tell you you are sick, but actually you are not really sick. So this will be like a companionship between AI and the health personnel to assess them to make a better prediction. So that's basically what this one will do. So we are trying to actually move from traditional kind of health where you go there, you tell the doctor you are sick, and he say, okay, maybe it's malaria or you are suffering from this disease, without doing actually any test or doing any kind of proper diagnosis. But with this kind of models which are being used in AI, it will get to a certain point that we can build better models. We can even sequence your gene and sequence these kind of viruses that are being rampant in our society. Then we can actually try to compare them. So if you come to the hospital, the doctor will tell you to go and do a test, then feed the results to the AI, then the AI will predict the kind of disease you might actually be having. And the doctor too can make an assumption and it will confirm or deny the initial thought he's having, instead of him just trying to say, look, based on your symptoms, maybe you might be having malaria, but actually you might not be having. So this is where AI is heading towards in health. And I think it's a sensitive area because we know that models are not perfect, right? So if they are not made perfect and they make a lot of errors, then it means people are going to get wrong diagnosis and people are going to die. So AI in health is very sensitive because we are talking about human life and we can't afford mistakes. So this area that is being studied, and people, researchers around are trying to better it so that humanity will be better, medicine will be better, everyone will be healthy, as we hope so. So basically this is what I can say. This is just an application, one application of everything we've been hearing since yesterday and today in health. We've done one in agriculture, and this is health sciences. Thank you very much.
Thank you very much, Emmanuel. We'll make time for questions.
Hello. Thank you very much for your presentation. I think your work was wonderful. I just want to find out, a lot of work in self-supervised learning I've seen have used contrastive losses. So what was the main motivation for using triplet losses, and how does it compare with the ones that use contrastive losses in terms of maybe computational and then stuff? And also, if your paper is already published, maybe you can share a link so that we can also read that.
Okay, so yeah, so basically they are all forms of constructive learning, and they all use similar losses, which is basically the idea is I explained about the CPC on all those things, they use it. But we also wanted to use something basically different from what anyone has also been trying to do. So it's not really like exceptional, but trying to do other things to see if it will help improve the performance of the basic unit. So basically, the ideology and everything is the same, but just like using different approach. But we use the triplet laws because we found the mathematics behind as a citing, just to at least just a mathematical, but because some of these AI models, you actually use them and it's like, some people see it as a black box, right? Like, we don't understand what's really going on. So just feed your data to the model, get an outcome. You don't care about what is going on inside. So something to at least explain or get something behind it. And we are still working on it. It's not published yet. So me and my supervisor and other things, we are still working to improve it more. So if it's out, we will let you know.
Oh, hi. On self-supervised learning, usually the sample procedure of the negative samples tend to bias the final representation. Could you describe how you choose how you sample negative examples when you train the triplets?
Oh, yeah. Okay. So what we did was, as I think I did it in one of the slides. What we do is we pick the images as batches, right? Then we form some croppings on them. So we crop the images. Then after doing all our argumentations with the deformation, so let's say right now, let's use one single image that's coming in our network, our encoder. The first image that's coming, we assume it as an anchor, right? Then after deforming that same image, we use it as our positive sample. Then we pick another image that is totally different from the first image as our negative example. So that is what we call the negative. So the negative sample is different from the first image, which is the positive, but the anchor, it's similar to the first image, which is our positive sample, but with a little bit of deformation. I don't know if you really get what I'm really saying.
Yeah, but for instance, ensure that the second negative samples came from a different patient. For instance, if the negative samples came from the same patient, there is likely a lot of correlation between.
No, yeah. So the 60 images are from different patients.
Okay.
So it's like 60 people.
Okay.
So the images are from, every image is from a different person.
Okay, thanks.
So there's a question from one of the participants online, and it says, please, must you have an insight about biology or human anatomy before helping in developing AI in health science?
Okay, I think it's a great question. I think question in, so you have to be experts. I'm not helping. Learn more from this. I think I felt like this is what I really want to do, to be involved community in terms of life. So I use the knowledge in biology that I learned from secondary school, and first I was taught and mathematicians, all these things, basic knowledge on it. But if you are in a group and you are working together, and there are people like in our group, at least the people from the health sectors, great us, your knowledge is important, but technical, you can learn who have more knowledge to help you in that field. Basically, so you don't have an expert, you have a lot of it.
Hello. Like actually rates lives. So this project, the model building needs to be like absolute perfection. So said the negative image, it needs to be a dissimilar image to the positive image. But again, asking how different would the image from the positive. You've taken a picture of the house. I don't think you might want to take the negative image of probably the limbs. So actually take a picture of the liver, which looks a bit similar to the heart, because your model your to be affected, because you have to deal with you. Asking how different is from positive to the negative image.
So if I understand what you were trying to say, the images that we are trying to consider here are images that are really in one particular group. So here the MRI is basically for the brain, the heart, lungs, or anything. So someone who is working, let's say, can take X-ray to see how much maybe the lungs, the organs are. So if it's an X-ray kind of problem you're trying to solve, you are trying to maybe that brain data set must be brain. Because generally, issue if working we have to solve, right? So try to stay for me. To have to stay
To better take up image
that brain and you need the which exercise can brain.
okay, so let me so will be image a positive will be what image a negative what image of the brain.
Okay,
Miss specifics.
you can go back to the images, the slides. Let's stay here, right? So here we can see that these images, right? This is an image, right? This is the same. They are the same. We can deform this, right? So it's the same image here. So this is from the same person. then we deform it. So this is the anchor, and this is the positive. It's just the same image that we've deformed it. This is an entirely different image from this, from a different patient. And we also deform it. So this will be our negative, which has really nothing similar to this one. Is it quite understandable? So let's say the anchor will be, let's say, me in this one, then me in a suit will be, let's say if me in this kind of traditional wear will be my anchor, then me in a suit will be something like a positive because it's the same me but in different shape. Then maybe you can be a negative. So this same triplet loss is used in facial recognition, an ideology about that, but we are trying to apply it in medical imaging. So with that person, if you train a model of me and my other images in different forms, then we can use you as a negative to also train with it. So at the end of the day, the goal is we are supposed to bring all images that look like me together with me, and images like you that don't look like me to be separated far from me. So that's the ideology we are trying to use here.
Okay.
Is
It's
okay?
understood, but I still have a little bit of. Okay, so my question is the anchor, the positive, and the negative are taken from one domain.
Yeah,
one domain.
The
But like,
data set must be
for instance, the brain.
Yeah,
All the images are taken from the brain.
Yeah, all images are from the brain. So all the images are like this. So what we want to know is, can you go to the last image? At the end of the day, we fed this kind of model into our network, and this was someone who labeled this image. This is a ground truth. The person labeled this image according to the expert, like the person has the disease, which is white matter hyperintensity. So this was the ground truth related to this image. Our model is supposed to predict something similar to this. So if the prediction is this, and this is the ground truth, it means this person has this kind of disease because the label of this is saying that the person has this disease because there is some white kind of matter which is being discovered in the brain of the person. So this is basically what you are trying to say.
Okay, I'll see you in chambers for more explanation.
Thank you very much. You can see.